Clipping is the process of eliminate. Yeah, one sec. Yeah. Clipping is the process of eliminating parts of objects or primitives that cannot appear on the display because they lie outside the clip volume or viewing volume. Okay. We are seeing through a camera of, we will not be able to see the entire view. We will be able to see only a part of the view. Okay. So what clipping does is it eliminates the parts of the objects which cannot be seen. Okay. Then we saw two-dimensional point clipping. That is, a point XY will be visible or will be seen in the window only if it satisfies these four inequalities. That is, XW min, is less than or equal to X is less than or equal to XW max, and YW min is less than or equal to Y is less than or equal to YW max. Okay, this is what we have seen. Next, we were seeing what is two-dimensional line clipping. Like if the line P1, P2 is to be clipped, how it looks. If both the endpoints are inside the window, the entire line will be seen. If the if the entire line is outside the window, then nothing will be visible. And if a part of the line, like your line P6, P5, P6 or P7, P8, if it is partly inside, then only that part of the line which is inside will be visible. The other part will be not visible. So the invisible part has to be clipped as it is shown in this diagram. Okay. And we said that the major goal for any line clipping algorithm is to minimize the calculation of the intersection points. Okay, because this is the only time consuming process and we want to minimize that. Any algorithm tries to minimize this. And we have two main algorithms. One is Cohen-Sutherland line clipping algorithm and the other is Liang-Barsky line clipping algorithm. In your syllabus, you have only Cohen-Sutherland line clipping algorithm. That is what we are going to see today. Now, this algorithm is one of the earliest algorithms to be developed for line clipping, and the processing time is reduced by performing more tests before proceeding to the intersection calculations. Yeah, we'll see these in detail. Now, what this algorithm does is you have, say this is our clipping window. Okay. Now, this is defined by four boundaries. This is the lower boundary, this is the upper boundary, this is the left boundary, and this is the right boundary. Okay, now Cohen-Sutherland algorithm, he extends these boundaries infinitely. What do we achieve? We divide the entire space into 9 regions. Okay, this region which is inside, which is bounded by the clipping window, is inside. Okay, that is the part which will be visible. Okay, now the remaining 8 regions which are outside are not visible, and whatever object falls on those 8 regions, they are to be clipped. Okay, yeah. Now, for each of these regions, a region code is given. Okay, it is called as either out code. It is called as out code or it is called as region code. Okay, so for each region, a code is given. Now, how is this code given? This code consists of 4 bits. B4, B4, B3, B2, and B1. Okay, so B4 bit corresponds to the top boundary line. You have this as the clipping window. Okay, B4 bit corresponds to the top boundary line. B3 bit corresponds to the bottom boundary line. B2 bit corresponds to the right boundary line, and B1 bit corresponds to the left boundary line. Okay, B1 for the left boundary, B2 for the right boundary, B3 for the bottom boundary, and B4 for the top boundary. Okay, now what does each of these bits mean? Bit means you have two values, 0 and 1. Okay, if the line or if the point is to the left of the left boundary, then that bit will be 0. Okay. Yeah. Once. Yeah. So we have this as the clipping window. We have 4 bits, B4, B3, B2, B1. Okay. This bit stands for the left boundary. Okay. Now, if a point is, this is our left boundary. If a point falls on this left side region, then the bit will be set to 1. Okay, for points which are to the right, that is this side, this bit will be set to 0. Okay, so bit 1 tells whether the point is to the left of the left boundary or to the right of the left boundary. Okay, now bit 2 is set to 1 if the point is to the right of the right boundary. Okay, you have the right boundary. If it is to the right of the right boundary, this will be set to 1. Okay, and bit 3 will be set to 1. Yeah, this is top, bottom, right, and left. Okay, so this bit 3 will be set to 1 if the point is below the bottom boundary. Okay, that is for this region. And bit 4 will be set to 1 if the point is above the top boundary. Okay, we'll see an example. So, okay, now we have divided it into 9 regions. Now the bits are given by the bit 1 is what is on the left. Bit 1 is what is on the left. Bit 2 is for the right. Bit 3 is for the bottom. And bit 4 is for the top. Okay. So now if you take the clipping window, the points inside the clipping window, okay, they are not to the left of the left boundary. Okay. So the bit 1 will be set to 0. Okay. Now these points are not to the right of the right boundary. So that bit is also set to 0. Okay. Now these points are not below the bottom boundary. So it is 0. These points are not above the top boundary. So that bit is also 0. Okay. So the outcode for the points inside the clipping window is 0, 0, 0, 0. Is this clear? Yeah, I think some people have not understood. I'll just explain it once again. Cohen-Sutherland algorithm does is this is our clipping window. We divide the entire region, the entire space into 9 different regions by extending the boundaries. Okay, now he gives outcode or region code to each of these regions, okay, to the 9 regions. Okay, the outcode consists of 4 bits: bit 1, bit 2, bit 3, and bit 4. Okay, now bit 4 stands for the top boundary, bit 3 for the bottom boundary, bit 2 for the right boundary, and bit 1 for the left boundary. Okay, now if the point is to the left of the left boundary, B1 will be set to 1. If the point is to the right of the left boundary, or it is not to the left of the left boundary, then it is set to 0. Okay, now bit 2 will be set to 1 if the point is to the right of the right boundary. If the point is not to the right of the right boundary, it will be set to 0, and so on. Okay, we will give the codes for each of the regions, then it will be clear. Okay, now when you come to the clip, to say this region that you have, this region. Okay, now what is the code that you have? Okay, the point is, okay, first we check the left boundary. Okay, this point is to the left of the left boundary. This is the left boundary. The point is left of the left boundary, so that bit is set to 1. Okay, now when you come to B2, it checks for the right boundary. Now the points in this region are not to the right of the right boundary, so that bit is set to 0. Okay, now these points are coming to the third bit. Now these points are not below the bottom boundary, so again it is set to 0. Okay, now these points are above the top boundary. This is the top boundary. They are above the top boundary, and so this bit is set to 1. So region code for this space, this region, is 1001. Is this clear? Yeah. Now, what about this region that we have? This region. This region. Yeah. Now, for this region, the point is not to the right of, not to the left of the left boundary. Okay, and so that bit is 0. Okay, now the second bit, when you take, these points are not to the right of the right boundary, and so it is 0. Okay, now these points are not below the bottom boundary, so it is 0. But these points are above the top boundary, and so it is 1. So the region code for this region is 1000. Is this clear? Yeah, fine. What about the code for this region that we have? Yeah, you can give me the answers in the chat box. Yeah, 1010 is correct. Okay. What about for this region? This is 1010. Yeah. So this region is 0001. This we have written as 0000. What about this region? Yeah. So for this region, it is 0010. For this region, it is 0, 1, 0, 1. For this, it is 0, 1, 0, 0. And for this, it is 0, 1, 1, 0. Is this clear? Yeah, good. I find, yeah, all correct answers. Yeah, so this is how the region codes are given. Okay, now when you write a program, okay, here in the example that we have taken, the way we have taken the clipping window, we are able to see the clipping window and we are able to give the region codes. Okay, but in a program, will you have this? We will not be having. Okay, what we will be given is, we will be given the clipping window with any rectangular region is identified by the bottom left point and the top right point. Okay, this would be XW min, YW min, and this is XW max, YW max. Okay, now given this and the coordinates of a point X comma Y, how will you know this region code? Okay, one way is you compare the value of X with respect to XW min. Okay, if X is less than XW min, then your bit 1 will be set to 1. Otherwise, it will be set to 0. Yeah. I have this as my clipping window. This is XW min, YW min. That is this point. This point is XW max, YW max. Okay. So my bit 1 is set to 1 if my X is less than XW min. That means if the point lies on this side of the left boundary, on this side of the left boundary, then the bit is set to 1. Otherwise, it is 0. Okay. Similarly, bit 2 is set if X is greater than XW max. That is, if you fall on this region. Bit 3 is set to 1 if Y is less than YW min. That is this region. And bit 4 is set to 1 if Y is greater than YW max. Okay. It is the same thing, whatever we have described. Now it is the form of an equation. Is this clear? Yes, some people are asking me to repeat. I'll just repeat. Okay. Now, when you are given, when you are asked to program, okay, in our case, our clipping window was a small one. We have just taken a small clipping window. So we are able to see the figure and we are able to give the region codes correctly. Okay. Now, suppose you have a huge clipping window which you are not able to see. Okay, you are only defining XW min, YW min, XW max, YW max. That is a clipping window. Okay, now how do you set the 4 bits? How do you set the 4 bits? Bit 4, bit 3, bit 2, and bit 1. Okay, this we have already seen this corresponds to the top boundary, bottom boundary, the right boundary, and the left boundary. Okay, so here, what is left boundary? All the points that lie to the left of the left boundary is, that is, this is the is going to be set to 1 for bit 1. Okay, so what is left of left boundary? How do you define this? This is this line is the line Y equal to XW min. Okay, so all the points to the left of this line will have X less than XW min. Okay, so for a given point X comma Y, for a given point X comma Y, if the X coordinate is less than xw min, then bit 1 is set to 1. Okay. Otherwise, it will be set to 0. Okay. It is the same thing, translation of whatever we have described in words into equations. Okay. Now, when is bit 2 set to 1? If the point is to the right of the right boundary. Okay. That means this is our right boundary. If the point lies in this region, then bit 2 is set to 1. Okay. When is the point to the right of the right boundary? What is the equation to the right boundary? Equation to the right boundary is given by x equal to xw max. Okay, so for points to the right of the right boundary, x would be greater than xw max. Okay, and so if x is greater than xw max, bit 2 will be set to 1. Okay, similarly, bit 3, that is for points below the bottom boundary. Okay, so the equation to the bottom boundary is given by y equal to yw min. So if the point xy has y less than yw min, then bit 3 is set to 1. And bit 4 is set to 1 if y is greater than yw max. Is this clear? Yes. Okay. Fine. We'll proceed. Another way of expressing the same thing, instead of taking as inequality in a program, comparing signs is much easier. Okay, so the same thing, we give it in another form. You have, we have this as the clipping window. Okay, we have the point x comma y. Okay, when is bit 1 set to 1? If x is less than xw min. Okay, then what is x? Means x is less than xw min, or xw min is greater than x, or xw min minus x is greater than 0. Greater than 0 means what? It is positive. Okay, so this bit will be set to 1 if the sign of xw min minus x is positive. Okay, that is, if you calculate the value of xw min minus x, if it is equal to 1, then, if the value is positive, then the bit is set to 1. Okay. If the value is negative, then the bit is set to 0. Okay. This is another way of expressing the same inequality. Okay. We have x, if x is less than xw min, then we are setting it to 1. Okay. Or you take the value of xw min minus x. If the sign is positive, you set to 1. If the sign is negative, you set to 0. Is this clear? Okay. Same way, bit 2 is set to 1 if x is greater than xw max. Okay, or the sign of x minus xw max. If it is positive, we take it as 1. If it is negative, we take it as 0. Same way for bit 3, we take the sign of yw min minus y. Okay, if it is positive, we take as 1. If it is negative, we take as 0. Same way, bit 4, if the sign of y minus yw max is positive, we take as 1. Otherwise, we take it as 0. Yeah, we'll go ahead. Sorry. Yeah. Okay. Now, this is the first diagram that we had seen. Okay, if the line P1, P2 we are taking. Okay, what is the region code for P1? Since it is, only thing is I have superimposed with the region codes that we have just calculated. Okay, so if what is the region code for P1? Since it is within the clipping window, it will have 0, 0, 0. All points inside this clipping window will have the code as 0, 0, 0, 0. Okay, now what is the code for P2? P2 also has a code 0, 0, 0, 0. Okay, so if for the line to be visible, if both the end codes are 0, 0, 0, 0, then the line is completely visible, and in our output window, the entire line would be visible. That is, we have to draw P1, P2 completely. Is this clear? Okay. Yeah. So for a given line, if the outcodes, we first calculate the outcodes. If the outcodes are 0, 0, 0, 0 for both the endpoints, then the line is completely visible and we will draw the line. Okay. Now we take P3, P4. Okay. They are falling, P3 is falling in this region, so its code is 0, 0, 0, 1. Now P4 is also falling in the same region. You have 0, 0, 0, 1. Okay. Since both are not 0, 0, 0, 0, that means P3 is falling outside the clipping window. P4 is also falling outside the clipping window. Okay. Now you take this line P5, P6. Okay. What is the code for P5? Since it is falling in this region, the code would be 0, 0, 0, 1. Okay. For P6, since it is falling within the clipping window, this region, the code is 0, 0, 0, 0. Okay. That means since the code is 0, 0, 0, 0, P6 is falling inside the clipping window. And for P5, since the code is not 0, 0, 0, 0, it falls outside. That means some point of intersection is there with one of the boundaries. Okay, we have to calculate that. Okay. Now, when you take P7, P8, P7's code is 0100, P8's code is 0010. Okay, this P7's code is also not 0000, P8's code is also not 0000. That means we will not be able to decide. The line is intersecting some of the boundaries of the clipping window. Okay, so we have to find the points of intersection and then decide. Okay, same way if you take P9, P10 also, this one's P9's code is 1001, P10's code is 0010. Okay, again, we will not be able to decide whether it is inside or outside. It depends on where it is intersecting. Okay, so we have to find the points of intersection and find out. Okay, now all that we know is, all that we are trying to understand is, if the point is inside the clipping window, the outcodes for both the endpoints are going to be 0, 0, 0, 0. Okay, if they are not inside, then you will have a different value other than all zeros. Is this clear? Yeah. We will be repeating this. I think one person has not understood. Okay, I'll just repeat it once again. Once. Yeah. So if you take P1, P2, the outcode for P1 is going to be 0, 0, 0, 0. since it is within the window. Okay, for this entire region, the code is going to be 0000. So for P1, the code is 0000. For P2 also, the code is 0000. If the codes for the two endpoints are 0000, then the entire line is visible, and in the clipping window, we have to draw the entire line. Okay, now when you take any other line like P3, P4, if you take, both the endpoints are not all zeros. So we don't know whether a point, the part of the line is inside or outside. Okay, we will not be able to decide. We have to calculate points of intersection and then decide. Okay. Now, if you take P5, P6, okay, for P6, the code is 0000, whereas for P5, it is 0001. Okay, so one point is 0000, then that means the point is, the line is partially inside. Okay, so we have to calculate the point of intersection, and from the point of intersection to this point P6, that alone will be drawn. That is, the line from here to here alone will be drawn. Okay, now if you take P7, P8, the outcodes are not all zeros. Okay, for both the endpoints, that is for P7 and P8. And so again, you need some more calculations. That is, you have to calculate the intersections, etc., and then decide. Okay, how we are going to decide is what Cohen-Sutherland algorithm is going to teach us. Okay, yeah. Now, so if the outcodes for the two endpoints are all zeros, then the line is visible and the entire line will be shown in the clipping window. Okay, that is what we understand from this discussion. Okay, now another point is, you take this line P3, P4. Okay, for both the points, the codes are 0001, 0001. Okay, you see that bit 1 is 1 for both the endpoints. Okay, if that is the case, that means the line is falling towards one side of the boundary, and that is outside the clipping window. Okay, now you take another line, say from here to here. Sorry. We take the line from here. One second. Okay. Now, what is the end code for this point? This is 0101. What is the end code for this point? It is 1001. Okay, what we find is this bit B1 is 1 for both the endpoints. Okay, what is bit 1 corresponding to? That corresponds to the left boundary. Okay, if the point is to the left of the left boundary, then this bit is going to be set to 1. Okay, and so that means the entire line is falling to the left of the left window, and so that can be totally rejected. That means in the output, we will not be showing that line at all. Okay. If the same bit is set for both the endpoints, then that line will not be shown in the output diagram. Okay. You take another example. Say we are taking this line. Okay. Then this code is 1000. The code for this point is 1010. Okay. So we see that this bit 4, is set as 1 for both the end codes. Okay, the outcodes for both the endpoints, the bit 4 is set. Okay, bit 4 stands for the top boundary. Okay, the bit 4 is set to 1 if the point is above the top boundary. Okay, that means since bit 4 is set for both the endpoints, the entire line lies above the top boundary, and so this line will not be shown in the output window. Is this clear? Yes, there is a doubt. If we decide if both the outcodes are all zeros, then the point lies within the clipping window and it will be shown in the output. Okay. If it is not all zeros, then some points of intersection will be calculated. Okay. That we will just see now. Okay. So right now, if the codes for the two endpoints are all zeros, then the point is inside and it is visible. Otherwise, we have to make some calculations. Okay. Yeah, we will see what calculations have to be done. Yeah, we take this example. We have the clipping window. We have the line P1, P2. Okay. What is the outcode for the point P1? Okay. You send in your answers. Outcode for P1. Okay, most are right answers, but there are a few wrong answers. I will repeat. Yeah, how we calculate the code for P1. Okay, we have 4 bits. Yeah, 1 second. Corresponding to top, bottom, right, left. Yeah, bit 1 is set if the point is below the bottom, is to the left of the left boundary. Okay, now this is, yeah, this is my right boundary. The left boundary is already shown. Yeah. So now for this point P1, this is my left. This is my left boundary. Okay. And this P1 is not to the left of the left boundary. So the code is 0. Okay. Now this point, this is my right boundary. P1 is not to the right of the right boundary. So that bit is also 0. Okay. Now P1 is below the bottom boundary. So the third bit is set to 1. Now P1 is not above the top boundary. So it is set to 0. Okay. So the outcode for P1 is 0, 1, 0, 0. Yes. Now calculate the code for P2. Yes. Most of the codes are right. Yeah. It is 1 second. It is the point P2 is to the left of the left boundary. So the bit is 1. The point P2 is not to the right of the right boundary. So it is 0. The point P2 is above the top bound, is not below the bottom boundary. So it is 0. And it is above the top boundary. So it is 1. The code is 1001. 1001. Is this clear? Divya, it is 1001. Okay? Yeah. Next, what do? We see that both the encodes are not all zeros. Okay, so we have to do some more calculations. Okay, what is the kind of calculation that we do? Okay, we take in any order. In our case, say we take in the order of, we take first the left boundary, then we take the right boundary, then we take the bottom boundary, and then we take the top boundary. Okay, so first we check if the left boundary bits are set. Okay, if we are going by this order, the order can be anything. Okay, if we are going in this order, we first check if the left boundary bits are set. Okay, now for P1, when you take, the left boundary bit is 0. Okay, whereas for P2, the left boundary bit is 1. So that means P2 is lying to the left of the left boundary. Okay, we have to truncate this line, okay, or we have to clip this line to the left boundary. Okay, we are not bothered about points lying outside the boundary. Okay, so we will push this point P2 to the left boundary. Okay, that is, say it is P2 dash. How do you get this? So we have to calculate this point of intersection. Okay, so we will clip this line P1 P2 to P1 P2 dash. Okay, what is P2 dash? The point of intersection with the left boundary. Why are we taking the left boundary? Because we are checking that the bit 1, the left boundary bit is set to 1. Okay, so we are taking the point of intersection with respect to the left boundary. We will truncate this line which is outside the boundary, and we will consider the line only from P1 to P2 dash. Understood? We are finding the point of intersection P2 dash, and then we will consider the line only from P1 to P2 dash. Is this clear? Okay, fine. Some people have not understood, some have understood. Clear? I'll repeat it again. Yeah. Now, when I am taking the two outcodes, the outcode of P1 is 0100, the outcode of P2 is 1001. Okay, now I am going in the order, the left boundary, right boundary, the bottom boundary, and the top boundary. Okay, so first I am considering the left boundary. Okay, now this left boundary bit is bit 1, and for P1 it is 0. Okay, for P2 it is 1, that is this bit. Okay, so what I do is I find the point of intersection for the line with respect to the left boundary. Okay, since the bit is 1, that means this point is lying to the left of the left boundary. So I will truncate this line up to the left boundary. So I find the point of intersection with the left boundary. Say that point is P2 dash. Okay, so now I will consider the line from P1 to P2 dash only. Okay, so P2 dash I have found, and I will truncate the line up to P2 dash. Okay, so I will clip out this line. My line will be from P1 to P2 dash only. Is this clear? Yes. Okay. Now I find out, since I have removed out this part, now I need to find out the outcode for P2 dash. What is the outcode for P2 dash? Okay, now P2 dash, if I consider, it is not to the left of the left boundary. It is on the left boundary. It is not to the left of the left boundary. And so the bit will be set to 0. Okay, now bit 1 is, it is not to the right of the right boundary. So again, it is 0. Okay, now this point is not below the bottom boundary. So it is 0. This point is above the top boundary. So it is 1. So the outcode for P2 dash is 1000. Is this clear? Yes. Okay. I said we are following this order: left boundary, right boundary, bottom boundary, and then the top boundary. Okay. Now, so left boundary we have finished. Next, we check with the right boundary. Okay, right boundary bit is this, the second bit 2. Okay, you find that for P1 it is 0, for P2 also it is 0. That means both the endpoints are not lying to the right of the right boundary, they are within the boundary limits. Okay, so we don't do anything. Next, we check the third bit. Okay, that is for the bottom boundary. Okay, now here for P1 it is 1. Okay, for P1 it is 1, whereas for P2 it is 0. That means P1 is lying below the bottom boundary, whereas P2 is not lying below the bottom boundary. Okay, what do? We clip this to the bottom boundary. That means we find the point of intersection between, for this line P1 to P2 dash and the bottom boundary. That is this point we find out. Okay, say that is P1 dash. Okay, and we remove out this from the line. That is, we consider the line only from P1 dash to P2 dash. Is this clear? Okay. Now, what is the code for P1 dash? Code for P1 dash? Yeah, it is all zeros. In considering the clipping, okay, we are considering the left boundary, right boundary, bottom boundary, and the top boundary. Okay, we have taken the left boundary, we have clipped it. Right boundary, we saw that both are zeros. Now we are considering the bottom boundary. Okay, now since this P1 is below the bottom boundary, we have clipped it to P1 dash. Okay, and now we have the line from P1 dash to P2 dash. Yeah. Now again we find the code for P1 dash. It is all zeros. Okay. Now again, so our consideration is, yeah, we are seeing first the left boundary we have checked, right boundary we have checked, then bottom boundary we have checked. Now we have to consider the top boundary. Okay. Now the code for the top boundary is bit 4, and that is 0. Whereas for P2 dash it is 1. That means P1 dash is not above the top boundary, whereas P2 dash is above the top boundary. Okay, so what do we do now? We have to find the point of intersection between P1 dash, P2 dash, and the top boundary. Okay, that is this point we find out. Say it is P2. Say it is P2 double dash. Okay, we find out that point, and we will consider we will clip out from P2 double dash to P1 dash, P2 dash. We will consider the line only from P1 dash to P2 double dash. Okay, now what is the code for P2 double dash? Yeah, for P2 double dash it is again all zeros. Okay, so now we see that the outcodes for P1 double dash is 0, 0, 0, 0, and for P2 double dash is also all zeros. We have already seen that if both the if the outcodes of both the endpoints are 0, 0, 0, 0, then the line is visible. So in the output, we draw this line from P1 dash to P2 double dash. Is this clear what we have done? Okay. Yeah, we'll see another example. So what we did was P1, P2 was our original points that was given. Okay, we found the outcodes. Okay, then we found that we both are not all zeros. So that means a part of the line is inside, a part of the line is outside. Okay, now means we have to do some calculations. What we did was we found the we started in the order left boundary, right boundary, bottom boundary, and then the top boundary. Okay, the left boundary, when we checked, P1 is, yeah, P1 is not to the left of the left boundary, whereas P2 is to the left of the left boundary by this one. Okay, so we clipped P2 to P2 dash. So we considered the line only from P2 dash to P1. Okay, this line. Then what we found was we tried against the right boundary. Okay, both the endpoints were inside the right boundary, so nothing to be done. Then we checked with respect to the bottom boundary. P1 is below the bottom boundary, so we clipped it to P1 dash. So now we considered the line from P1 dash to P2 dash. Okay. Then again, we checked with respect to the top boundary. We found that P1 dash is not above the top boundary, whereas P2 dash was above the top boundary. And so again, we clipped it to P2 double dash. That is, we considered the line from P1 dash to P2 double dash. The entire line is visible and we are drawing it. Yeah. Now the next example we see is this P3, P4. Okay, what are the codes for P3 and P4? Okay, calculate the outcodes for P3 and P4. Yeah, you can calculate the outcodes for P3 and P4 and send in the chat. Yes. For P3, it is 0101. For P4, it is 0100. Okay. Again, we take the same order. We are first considering the left boundary, right boundary, the bottom boundary, and the top boundary. Okay. So when we see the left boundary, okay, this is P4 is 0, whereas P3, the bit is 1. Okay, so we clip P3 to this point, P3 dash. That is, we find the point of intersection with the left boundary. Okay, now what is the code for P3 dash? Zero 1 0 0, right? And we will clip out this part. We will have only from P3 dash to P4. Okay, we have P3 dash. The code is this. Okay. Now again we check. We have checked the left boundary, right boundary. When we see, it is all zeros, so no problem. Next, we see the right boundary. Okay, that is the third bit. Third bit is 1 for both the cases, P3 and P4. That means the entire, both the points are falling below the bottom boundary. Okay, so the entire line will not be visible and our output will be like this. That is, the entire line will not be seen. Okay, is this clear? Yes. So this will be the output, nothing will be seen. Yeah. Next, what we have to do is, how do we determine the boundary intersection for a line segment? Okay, that is, you have this line x naught, y naught, and this is x end, y end. You have this as the left boundary. Okay, or in general, I will take this as the equation to this line as y equal to mx plus c. How do I find the point of intersection between this line y equal to mx plus c and this line whose endpoints are given by x naught, y naught, x end, y end? Okay, I substitute x naught, y naught into this equation y equal to mx plus c. What do I get? Y naught equal to mx naught plus c. Okay, or c equal to y naught minus mx naught. Okay, I substitute this in the first equation. So I get y equal to mx plus y naught minus mx naught. Or this is equal to y naught plus m into x minus x naught. I'm taking m common here. So I get y equal to y naught plus m into x minus x naught. Is this clear? Yes? Yes. What is the value of m? M is the slope of the line. Okay, so m, one second. So m would be given by y end minus y naught divided by x end minus x naught. Okay, now I substitute this value in the previous equation. Okay, m equal to y end minus y naught by x end minus x naught. Okay, now if I substitute this value here, then I will get x equal to x naught plus y minus y naught by m. Right? Yes? Okay, I will do it. I have y equal to y naught plus m into x minus x naught. Okay, or y equal to y naught plus y end minus y naught divided by x end minus x naught One second, one second, one second. I have y equal to y naught plus m into x minus x naught. Okay, or m into x minus x naught equal to y minus y naught. Okay, or mx equal to y minus y naught plus m into x naught. I'm taking this minus mx naught that side. Okay, or x is equal to x naught plus y minus y naught divided by m. Mx naught I'm taking first, divide by m plus y minus y naught by m. Okay. Is this clear? Yes.
Ma'am, sorry for interrupting. Ma'am, it's time up.
Yeah. I'm just finishing this. Okay. So these will be the equations. Y equal to y naught plus m. Just note down these two equations. Y equal to y naught plus m into x minus x naught, and x is equal to x naught plus y minus y naught by m. Okay, these are the equations that we will use for the calculation of the intersection points.